So today we begin the third module, that is semi-classical bulk transport, electromagnetic field and transport equations. So far we have discussed the semi-classical transport from a qualitative point of view without using intricacies of any equations. So in which we intuitively visualized the phenomena associated with semi-classical transport. Now we will use this understanding to write down equations which will be solved to estimate the current flow in a device. So let us first list out what we want to achieve in the course of this module. So at the end of this module you should be able to write the equations of electromagnetic field driving the device current. So these equations are Maxwell's wave equations and their quasistatic approximation and the Lorentz force equation. Then you should be able to recognize the four approaches of determining the device current developed out of the individual carrier and ensemble viewpoints, in each of which the carrier can be treated either as a particle or as a wave. So you have individual carrier viewpoint and ensemble viewpoint of estimating the device current, and for each of these viewpoints you can treat the carrier either as a particle or as a wave. So overall you have four different approaches of calculating device current. Then you should be able to recognize that the equations of carrier transport in semiconductor devices have a common form which manifests conservation of some physical quantity. Now whenever students are faced with a number of equations, many of them get frightened. They do not like to see many equations. Now this is where this particular point is important. We will find that most of the equations which are used in modeling of carrier transport or modeling of devices have a common form. So once we recognize that they have a common form, then we are much more comfortable with the equations. Then you should be able to write the fundamental equations of determining the device current based on each of the following, namely the Schrodinger's equation, Newton's second law and Boltzmann transport equation, abbreviated as BTE. Next you should be able to write the equation for lattice temperature or heat flux and recognize its necessity for determining the device current from the ensemble point of view. Then you should be able to derive the approximations of the BTE, that is Boltzmann transport equation, namely carrier momentum and energy balance equations, drift diffusion and thermoelectric current equation. In the qualitative discussion we have remarked that you can analyze the current flow in a device using conservation of mass, energy and momentum, or in the parlance of semiconductor devices, carrier balance, momentum balance and energy balance. So we are going to write down equations for this purpose, and in the qualitative model we have also discussed about the three mechanisms of transport: drift, diffusion and thermoelectric current. So we would like to write down expressions for these as well and show how you can derive them from fundamentals. Finally you should be able to apply the balance equations to derive expressions for the velocity field and velocity overshoot characteristics. So ultimately the goal of writing all these equations and understanding all these equations is that we must be able to use them and derive expressions for the current in the device, which depends on the velocity. So therefore if you can write expressions for velocity field and velocity overshoot characteristics as a function of time or distance, then you can model the current flow. So let us first start with the organization of equations and boundary conditions. Whenever we talk of equations we must not forget about boundary conditions. So the equations for carrier transport are in general differential equations. So whenever you want to solve these differential equations you need boundary conditions, okay. So we have to always see the equations together with boundary conditions. So the two sets of equations are electromagnetic field equations and transport equations. So the electromagnetic field equations give you the electric field and the magnetic flux, and also the force on an electron due to these two, and these then help to drive the current. And so the transport equations tell you how, if you know the electric field, magnetic flux and the force on an electron, you can derive the current. So this is shown here pictorially. The arrow shows that electromagnetic field equations yield in their solution the values of B, E and F. B is the magnetic flux, E is the electric field, and F is the force on the electron due to electric and magnetic fields. Now the transport equations, on the other hand, estimate the current density for electrons and holes, abbreviated here as Jn and Jp. So these current densities are obtained taking these quantities as inputs, B, E and F. You also get the carrier concentrations for electrons and holes, which together with the impurity concentrations or doping level give rise to the value of the space charge. So space charge is given by this equation, Q into P plus Nd plus the total positive charges minus N minus Na minus. So these are the negative charges. Now this space charge and these current densities are required in the electromagnetic field equations to estimate B, E and F. The current densities, for example, tell you what would be the static magnetic field around the current, right? And similarly the space charge will contribute to the static electric field here. So that is how these quantities are required in the electromagnetic field equations. So you see that this is a coupled situation. Electromagnetic field equations gives you B, E and F, which are required in transport equations, and transport equations yield Jn, Jp and rho, which are required in electromagnetic field equations. So that is why the equations of semiconductor device are coupled to each other. They have to be solved simultaneously. Now let us look at the boundary conditions. So this is an example of a device where you have two contacts, one here and one at this end, and also it is extending on the side a little bit. So we need to know what are the values of these quantities B, E, F, Jn, Jp and rho at the boundaries of this device. So you can separate the boundaries into contacts and non-contact regions. So that is what is shown here in the slide. So the applied electric field, magnetic flux and heat flux impose conditions on various fluxes at the contacted and non-contacted device boundaries. Now let me just clarify where is the equation for heat flux. So you see here the equation for heat flux is absorbed in these transport equations. Now let us write the electromagnetic field equations. You have already done a course on electromagnetic fields, so you should be able to write these equations very easily. So first is a modified Ampere's law, which relates the magnetic field to the various current densities. So the two current densities here are conduction current density and displacement current density. Now the word modified here actually refers to the inclusion of the displacement current density. Now this is the great contribution of Maxwell. So without this displacement current density you cannot predict the existence of electromagnetic waves in vacuum or free space. Next is a Faraday's law of induction, which relates the electric field caused by the changing magnetic field changing as a function of time. Curl E is equal to minus dou B by dou T. The modified Ampere's law is curl H is equal to Jn plus Jp, which constitute the conduction current, plus dou D by dou T, which is the displacement current. Then you have the Gauss's laws, which tell you how the fluxes, namely the displacement flux D and the magnetic flux B, are affected because of various quantities. So for instance, divergence of D is rho. So this tells you that positive or negative static charges are sources of the electric flux. Divergence B is equal to 0. This tells you that really there is nothing analogous to the positive or negative charges in the context of electromagnetic fields. So you cannot have an isolated north or south pole, right? Whereas you can have an isolated positive or negative charges. So next you have the constitutive relations, which relate the displacement, the electric displacement to the electric field E via the permittivity of the medium epsilon, and the magnetic flux B to the magnetic field H via the permeability. Then you have the Lorentz force equation, which relates the force on the charge Q due to electric field and the magnetic flux. So V is the velocity of the charge. So F is equal to Q times E plus V cross B. If the charge is an electron, then Q will be replaced by minus Q. So the electromagnetic field equations actually consists of the 4 Maxwell's equations and the Lorentz force equation. So these together constitute the electromagnetic field equations. Now look at the next slide. Here we have written the Maxwell's electromagnetic wave equations in terms of B and E. So the previous slide consisted of equations written in terms of magnetic flux B, the magnetic field H, the electric flux or displacement D, and electric field E. Now since there are constitutive relations which relate D to E and B to H, we can write all the equations in terms of one quantity for the electric field or electric flux and another quantity for magnetic field or magnetic flux. Okay, that will make things simple. Also, you know that you can remember an equation well in your memory if you know the physical significance of the equation. So that is what we have written out in this slide. For each equation, what is the physical significance? So divergence B equal to 0. Meaning of this is B has no beginning or end, that is B is entirely circulating, or there are no isolated north or south poles. Curl B equal to mu times Jn plus Jp plus mu epsilon into dou E by dou T. Circulating magnetic field is created around conduction current density and time varying electric field. So that is the meaning of this. Okay, so basically this equation tells you the source of the magnetic field or the sources. So magnetic field is created both by conduction current and displacement current. Also, since it is a curl, it means that this B is circulating and circulates around J conduction and time varying E. So that information is also important. So if there is a current like this then around this the magnetic field will be circulating, right. So if this is J conduction, then this is B. Similarly, if there is an electric field like this and it is changing with respect to time, dou E by dou T, then also there will be a circulating magnetic field around it. So this is what is meant by this equation. Let us look at the equation for the electric field. So divergence of epsilon E is equal to rho. This means that E begins on positive charges and ends on negative charges. So that is what you derive from this equation, or positive charges are sources of E and negative charges are sinks of E. So if you want to show this pictorially, suppose the field is in this direction and here you have positive charges, then when I move to the right hand side of this, I would have got extra field lines emanating from the positive charges. So these positive charges act like sources. On the other hand, somewhere here, if there is a negative charge, it will sink the field line. Each negative charge will sink a field line. So if I pass this region and come out, I would have lost a field line. Okay. Now the accounting of all this is what is done in this particular equation, divergence of epsilon E equal to rho, divergence B equal to 0 and divergence of epsilon E equal to rho, both these are the Gauss's laws. Now curl E is equal to minus dou B by dou T. So this is an equation which tells you what is the source of the electric field. Apart from static charges rho, the electric field also is created by a changing magnetic field. So circulating E is created around time varying B. So again one can draw a diagram similar to this, that if there is a magnetic field something like this at any point, then around it there will be a curl. However, there is a negative sign in the relation and therefore the direction of the circulating field will be opposite to that what you get here. So if this is, then I am sorry, this is dou E by dou T, this is dou B by dou T, and this is what is the circulating electric field around the changing magnetic field. Finally, of course, you have the Lorentz force equation. Here also it is in terms of E and B. So we shall use the equations in terms of E and B. We have already clarified in the qualitative discussion of the model why we choose to use B, or rather why we choose to use E, electric field, instead of the displacement D, because it is electric field E which enters into the equation for the device current as well as in the equation for the force on the charges, that is the Lorentz force equation, whereas it is B which enters into the force equation. So therefore we are using E and B. Now before we proceed further, just we want to make things concrete and tell you that we are considering the current flow in a device as a consequence of all these driving forces. So this is the resistor, and supposing I have a changing voltage source changing with time, right, AC current. So in this case, as we have remarked during our qualitative understanding, that when the frequency is high, you have both electric and magnetic fields here and both are varying with time. Okay, so that is the kind of situation that we are considering here. An assignment for you: derive the electromagnetic travelling wave equations one for E and another for B in vacuum from the 4 Maxwell's equations. So if you do this exercise, then you will become much more comfortable with these Maxwell's equations. Now let us write out the Maxwell's equations and see what approximations can be made for the purpose of analyzing semiconductor devices, so that we can simplify the modeling. We have already mentioned about these approximations in the qualitative reasoning. Here we are putting down the equations and actually showing what terms can be ignored in the approximations. So these are the electromagnetic field equations written in this box here, and the arrows here indicate that B and E are fed as solutions of, are obtained as solutions of these equations, Maxwell's equations, and fed into the transport equations. Similarly, the Lorentz force equation gives you the information about the F. E and B are obtained from the Maxwell's equations and then fed into the Lorentz force equation. The transport equations, on the other hand, yield Jn, Jp and rho, and this information is required here. As you can see here, if I want to get the magnetic flux B, I need Jn and Jp, and that is obtained from here. Similarly, if I want to solve this equation for the electric field, I need rho, which is again given by the transport equations here. Now we will first discuss about the equations of the electromagnetic field and their approximations, and then do a similar exercise for transport equations. So first we make the quasistatic approximation. This means we are neglecting the changing electric field here, or the displacement current, and the changing magnetic field here. Time varying electric and magnetic fields are neglected. Now it is important to note that whenever we neglect a term, you should not assume that that term is absolutely 0. It is not as though we are setting that term to be 0. We must always compare that term with the other terms present in the equation, and so long as the term we are neglecting remains much smaller than the other terms, you can neglect it. For example, here when we say that this quantity is negligible, does not mean this is exactly 0. All that it means is this is much less than either this quantity or this quantity. Now this point is important to note. So we should not assume that E is completely static. It is not at all changing with time. It may be changing with time, but its rate of change is not very high. Now how do you decide whether it is high or not? It is again not an absolute number. It depends on the situation, and the situation as described by the other terms. So let me emphasize this point a little bit more, because the students often have confusion here. You see, supposing I consider the equation 100 minus 98 is equal to 2, or let me write it in this form: 100 is equal to 98 plus 2. Now if I neglect this 2, it is not a bad approximation, because 100 is indeed equal to approximately equal to 98 within 2% error. On the other hand, if I take an equation in which the same 2 appears, say something like this: 3 equal to 1 plus 2. Now if I neglect 2, I would end up saying 3 is approximately equal to 1. Now this is evidently grossly inaccurate, okay, because 1 is 1/3 of 3. So we cannot make the approximation here. So whether to neglect 2 or not depends on the equation in which this quantity appears, right, other terms. So this point should be borne in mind. The consequence of quasistatic approximation is that the time varying electric field is removed here and time varying magnetic field is removed, as a result of which curl of E becomes 0. So what we are saying is curl E is equal to minus dou B by dou T. This quantity we neglect. So in other words, we are saying this is. Now from the electromagnetic fields course, you know that if the curl of a vector is 0, the vector can be written as gradient of a scalar. In this case the electric field is negative gradient of the potential psi. Now at this point I want to just caution you that since there are many quantities used in this particular course and we do not have as many different letters to indicate these quantities, sometimes some symbols will be used for meaning different quantities. So from the context it will be clear what that symbol means. For example, in one of the earlier lectures I have used the symbol a, smaller lowercase a, to indicate the distance between the lattice atoms or lattice constant, right, and also to indicate acceleration, force by mass. Similarly here psi is used to indicate the potential. Later on when we talk about Schrodinger equation, the same psi symbol may denote the probability amplitude function which is used in Schrodinger's equation. From the context it will be clear what does the symbol mean. Now since you can write E as negative gradient of potential, you can modify this Gauss's law. If you substitute E equal to minus grad psi in Gauss's law here, you will get an equation del square psi is equal to minus rho by epsilon. So we are using this approximate sign to indicate that this is an approximation when the time varying magnetic field is neglected, right. So here similarly here also there is an approximation because time varying electric field is neglected here. One more thing to be noted here is that strictly speaking I can write del square psi as minus rho by epsilon only if epsilon is not varying with x. So in this quantity I am taking the epsilon out, so this means epsilon is a constant with x. Now this is the assumption that we will be making in this course, that epsilon does not vary with x. This del square psi equal to minus rho by epsilon is called the Poisson's equation. Next let us neglect the result of B or the effect of B. So what we are doing here is this V cross B term we are neglecting, effect of magnetic field is neglected. Now before I proceed further you might just wonder how this V is determined. So in fact this V can be determined from the information about the current densities Jn and Jp. So for example if you want to calculate the force on the electron, then V corresponds to the velocity of the electron. That can be obtained from Jn because we know that Jn is product of minus q times the concentration times the velocity. So since I know the concentration n and the concentration p and I know the current density Jn and Jp, I can easily derive the velocity as ratio of Jn to concentration, and we also divide out the charge. So this is how the V can be determined if we are interested. Now proceeding further with the approximation, if once we remove this term, we are not considering the effect of magnetic field on the electron, so force due to magnetic field on the electron is neglected. We really do not need these two equations, divergence B equal to 0 and curl B equal to mu times Jn plus Jp. So these go out of the picture, that is why they are crossed out here, and this B also goes out of the picture. Now once this equation has gone out of the picture, you no more need Jn and Jp to solve the field equations. That is why here the Jn and Jp arrow has been terminated outside the block. So this information need not be fed in to the Maxwell's equations. This information is however required because in fact our aim in modeling is to calculate the current density, right. So there we need Jn and Jp. So what we have achieved is that because of neglecting of B, we no more have to couple the transport equations and Maxwell's equations through Jn and Jp. So that coupling has been removed. So this is a considerable simplification. Now here is the summary of the equations with these approximations, the quasistatic approximation and neglect of B. E is equal to minus grad psi. This is the approximation of the curl E equal to minus dou B by dou T equation. Then divergence of epsilon E equal to rho, that is the Gauss's law, or del square psi equal to minus rho by epsilon, that is the Poisson's equation. Now we are retaining both forms of these equations because sometimes it is easier or necessary to find out the electric field from the space charge, in which case the Gauss law form is useful. On the other hand, sometimes we would like to relate the potential to the space charge. Okay? So at that time the Poisson's equation form is useful. The force on the electron is given by not exactly electron, force on the charge q is given by F is equal to q times E, or since E is given as negative gradient of psi, force is equal to minus q times gradient of psi. So these are our electromagnetic field equations, only 3 of them. Now rho, the space charge which is required to solve this Gauss law or Poisson's equation, is actually of the form rho is equal to q times p plus nd plus minus n minus na minus. So really if you know the electron concentration and the hole concentration, then you know rho. That is why what we are doing now is including that rho equation along with the Maxwell's equations, and instead of rho we now show the electron concentration and hole concentration as inputs to the field equations, and these are obtained from the transport equations. Now with that we have completed the discussion on the electromagnetic field equations. So we would like now to discuss the transport equations. As the comment made here shows, a range and hierarchy of equations exist for obtaining electron current density, electron concentration, hole current density and hole concentration, unlike the case of electromagnetic fields whose equations are standard. Here you can see that the output of transport equations is Jn, Jp, n and p. Now the reason why you have a hierarchy and multitude of equations is the following. The situation in a semiconductor device is very complex. So you have millions of particles, electrons and holes moving about randomly, and also a directed motion is superimposed over this random motion, and these particles are colliding with phonons, photons and impurity atoms which themselves are randomly located. So the situation is fairly complex. So once you have a complex situation, there are different ways of simplifying this picture, and that is why you have a range of equations. Okay? So the problem of flow of charge in a semiconductor is much more complex than, let us say, a two body collision that you might have studied in physics. So here it is a multi body collision and multitude of collisions. Now once we have said that the number of equations exist for describing carrier transport, many students get frightened and they feel, oh, they have to deal with a large number of equations. Now this is where this point that we are making now is very important. As the slide says, the variety of equations of carrier transport represent continuity or conservation or balance of some physical quantity. Hence they have the same form as, for example, the familiar hole continuity equation. So that is dou p by dou t is equal to minus dou by dou x of Jp by q plus Gp minus Rp. So here the equation is written in one dimensional form. It has a time derivative of hole concentration on the left hand side and the spatial derivative of the hole current density on the right hand side, and this is the generation rate, the excess generation rate, and Rp denotes the excess recombination rate. So this continuity equation of holes you would have come across in your first level course. Now what is interesting is that many of the equations of carrier transport that we are going to discuss will have this kind of a form. So let us understand the form of the hole continuity equation and see how you can extract some general patterns out of this. So one way of looking at the continuity equation or interpreting the continuity equation in words is the following: dou p by dou t, it represents the rate of hole increase in a small volume at x. Let us draw a diagram to illustrate this point. So let us say this is some x and you are looking at a small volume dx. Now this is one dimensional, so when we refer to a small volume, what it means is that there is a cross sectional area that is in this direction, right? And however the quantities are only varying in x direction. So when we are talking about the volume here, so it means this is the volume. So within this volume or within this region of thickness dx, the rate of change of hole concentration is dou p by dou t. Now why would the hole concentration increase in this region? So as this next term shows, the right hand side tells you the contributions to the rate of hole increase. So one contribution is the net influx of holes into the volume. So here there may be some holes moving in and some holes moving out. Suppose this is Jp of x and this is Jp of x plus dx. Now this can be different from this. So this difference may be responsible for increase in the hole concentration or decrease. So if Jpx is more than Jpx plus delta x, then there is a net input of holes. So this term you will represent as Jpx minus Jpx plus dx, and you will divide it by q because here you are talking of only the concentration and not the charge. Now further look at the dimensions here. This is per centimeter cube, and since there is a per unit time per second, now if I write the units for this, current density is coulomb per centimeter square, ampere per centimeter square, and that is coulomb per second per centimeter square, and that coulomb and this q will cancel, and so this will be per centimeter square per second. So you see there is a length dimension which is missing here, and that is because if you are talking of input of the rate of increase of holes within this volume, it will depend on this distance dx. If dx is more, there will be more holes inside. So here we have to multiply this by dx when we are writing the equation. Okay, so when we do that, this will also become per centimeter square. Okay, and in addition you can have generation inside the volume or recombination. So that is represented here by the terms Gp minus Rp. So Gp will cause an increase in hole concentration and Rp will cause a decrease. Now again unit of this is per centimeter cube per second. So you have to multiply this again by dx to get per centimeter square. So dx is more quantities will be, more holes will be generated. Now if you divide throughout by dx, then this dx gets cancelled, and now this term for dx tending to 0 is nothing but, so this term you can identify it as dou jpx by dou x with a negative sign, because dou jp by dou x will be jpx plus dx minus jpx by dx. Now we are putting a partial derivative here because things are changing with distance as well as with time. So while this is a derivative with respect to time, this is a derivative with respect to distance. So this is what is shown here. This term is net influx of holes into the volume plus this quantity is net rate of hole increase within the volume due to generation recombination processes. So you realize that this is a conservation, balance or continuity equation. So this is the form of the hole continuity equation. We will find that many of the transport equations are actually continuity, balance or conservation of some physical quantity. So you will replace the whole concentration of this continuity equation, whole continuity equation, with the appropriate quantity to get the other transport equations. So here is a generalization of the form of this equation. In general terms, we can say the time derivative of a quantity, here it is P, is there on the left hand side of this equation, and right hand side you have spatial derivative of the quantity's flux. So Jp is the flux of P, and time rate of generation or loss of this quantity. So Gp and Rp together, this is a net generation or loss of P per unit time, per unit volume. Now let us look at some further things about this equation. In what way can the flux Jp be written? So before we look at that, just let us put down the 3D version of this continuity equation. So dou P by dou T is equal to minus divergence of Jp by Q plus Jp minus Rp. So this is the 3D version. So this dou by dou x is replaced by divergence. Now this is where we consider the representations of flux Jp. So one way you can write Jp is Jp by Q as the whole concentration into velocity, or the quantity into the velocity of the quantity, or as in diffusion. For example, if the current is, whole current is because of diffusion, that is, it is because of gradient of the quantity, then you write it as minus the gradient of the quantity, that is holes, into a coefficient or constant, minus dp in this case. So if such a form for the flux is used, then the divergence term comes out as this form. So divergence of Jp by Q with a negative sign, that is what you have here, is equal to dp into del square P. So your flux term on the right hand side can be either of the form the quantity into its velocity, the quantity on the left hand side into its velocity, or del square of this quantity P, but with a positive sign and some coefficient over here. Now sometimes the time rate of generation or loss is assumed to be proportional to the quantity. So this term here, Rp, for example, from the first level course you would know it is written as P minus P naught by minority carrier lifetime. So you can generalize it by saying it is equal to this quantity P, in general this quantity minus a reference quantity by a time constant. So this kind of form is used to represent the loss of the quantity. So these aspects, that is how the flux can be expressed either as quantity into velocity or as del square of the quantity, and how the loss can be expressed as the quantity divided by a time constant. So these features will be generalized, will be used to write other equations. So once we can cast all other equations that we discuss in this form, you will appreciate that it is not at all difficult to remember all these equations. In fact, given a new situation, if you are asked to write an equation and you can recognize that equation to be a balance, conservation or continuity equation, you will be able to write the form of the equation by intuition after a knowledge of from a knowledge of this discussion. So towards the end of this lecture, let us make a summary of the key points. So in this lecture we started discussion of the equations which should be solved to derive the current in a semiconductor device. So we discussed the arrangement of these equations or organization of these equations, and we said that you can separate these equations into two sets. One set is the equations of electromagnetic field and the other set is the equations of transport. So these two sets are coupled because the equations of electromagnetic field need a knowledge of device current, or rather electron and hole current densities and space charge. On the other hand, these quantities are obtained from the transport equations, and the transport equations themselves need knowledge of the electric field, the magnetic field and the force due to these fields on the electron or hole charge, and this is given by the electromagnetic field equations. So you have therefore two sets of equations coupled to each other. And then we also emphasized that the equations should be seen along with the boundary conditions. So the field equations and the transport equations are both differential equations which have to be solved subject to some boundary conditions. So what are the conditions on electric field, magnetic field, the heat flux, then Jn, Jp and so on at contact and non-contact boundaries? This knowledge is also important. After discussing this organization, then we went on to describe the equations of the electromagnetic field in detail. So we said there are 5 equations which include the 4 Maxwell's equations and the Lorentz equation which gives you the force due to electric and magnetic fields. Then we discussed approximations of these equations. We said that if you neglect the effect of B, you neglect the force on the electron or hole due to the magnetic field, then 2 of the Maxwell's equations just drop out and you are left with only the 2 remaining ones. Now these 2, curl E is approximately equal to 0, and the Gauss's law which says divergence of D displacement is equal to rho. Now since in the quasistatic approximation the curl E is 0, E can be expressed as negative gradient of a scalar quantity, that is the potential. So therefore we can derive the equation the electric field from the potential applied, and there are no circulating electric fields. Similarly, because of the expression of E in terms of negative gradient of psi, the Gauss law which is divergence of epsilon E is equal to rho can be written in the Poisson's equation form as del square psi equal to minus rho by epsilon in terms of the potential. So you can relate potential to the space charge, and the Lorentz force equation becomes very simple. The force on an electron is equal to negative q, which is the charge on the electron multiplied by the electric field. Now after discussing the equations of electromagnetic field and their approximations, Then we started the discussion of the transport equations, and then we pointed out right in the beginning that though you will have a large number of equations, because there are different approaches of solving the complicated problem of carrier motion in semiconductors, most of these equations have a common form which is the same as the form of the whole continuity equation which you were introduced in the first level course. So this form consists of a time derivative of a quantity on the left hand side, and on the right hand side the negative gradient of the flux, negative divergence of the flux of this quantity, and rate of loss or gain of this quantity also. And this form of the equation will be repeatedly seen in the various transport equations that we discuss in the next lecture.